Unit 3 is all about explainability methods for images. In our last unit, we learned about the explainability methods for tabular data, which means structured data. These are the methods. First one, we need to understand what is ROI, region of interest. And from second onwards, we will find various methods to explain in the sense here that identify the regions of the image that has led to the prediction of that particular class. Lime, vanilla gradients, input by gradients, guided back propagation, grad cam, guided grad cam, smooth grad, deep lift. These are the various methods. If you look carefully, observe this slide, you can see that every method has a different way of giving the explanation. Here in Lime, um, it works by creating perturbed supersamples and giving us the how Lime works. It creates a simpler model and run it, and then gives us questions which are treated to be the explanation cues or the values. Whereas from method number 3, if you observe, every technique will give us some kind of visual output as explanation mechanism. Okay, the explanation itself is visual. In our last class, what we learned was that the explanation output was some kind of number and some kind of weight, importance score. Means it was more of a quantitative output. Whereas here, the output itself is a visual image, and our input is also an image. The output of vanilla gradients is a saliency map highlighting some of the regions. This is also some kind of edges, contours, and lines will be drawn here as a output. Here for guided back propagation as well, we'll find some kind of feature maps. And here this is called as heat map, where you use colors to indicate that this is the region which is very prominent in the prediction. And guided grad cam is combining grad cam and guided back prop. Here fifth technique and sixth technique. When you combine both of these, you get the seventh. And this is another technique, smooth grad. This output also you can see some kind of a feature map, and deep lift is also here. It is a visual explanation output. Here the goal is explain the deep learning predictions by identifying where and what in the image influenced the model's decision. So this is the region that has influenced. Here also it is saying this is the region. Here this is the region. Last class we learnt about ROI. Just a quick recap. ROI is the portion of an image that contributes most to the model's prediction. In this entire image, what is the area that is contributing most in the prediction of the class? Here CNN, which stands for convolutional neural network, is giving the prediction as cat with a confidence level of 99%. Now we want to know using various different techniques, what is the region in this image that has led to this class prediction. Let us look at LIME. LIME, as you know, it stands for Local Interpretable Model Agnostic Explanations. LIME explains one image prediction at a time. Therefore, it is called as a local method. It divides the image into superpixels. Well, now the question here is, what is a superpixel? It is collection of individual pixels. If you can observe here in this image which I am pointing, is having the sections or the portions or the regions divided by combining a set of pixels. Each such region or each such area is called as a superpixel because it is a combination of multiple pixels. And how it works, the strategy it uses here is it turns some superpixels on off, which means it perturbs. Perturbing here means if you have 10 superpixels, it makes use of only 5 superpixels for the prediction and rest 5 are hidden, or they are also called as masked. The other 5 are masked and only 5 are used for prediction. And next it continues this process. It divides let us say the image into 10 superpixels. Instead of 5, now it chooses 6, later 7, later 3, 2 by masking some of the superpixels and unmasked or on superpixels means the pixels which will be used for prediction. Using this process, it learns a simple interpretation model around the prediction and it provides local explanations. The same formula, same as tabular LIME. It is trying to minimize the loss. Loss with respect to the F is the complicated model or the black box model. G is the simple model. And then you measure the loss of that. Here you can see the locality weight, some weight you specify with respect to this X. And here you see this complexity penalty. It keeps model simple. Some kind of penalty like regularization technique will be there, no? Lasso, ridge. In that similar form, here also we have a penalty. And let us look at the procedure. Superpixel representation LIME first divides the image into n superpixels. They are represented like this. X is a image, S are the superpixels, S1, S2, S3 up to Sn, and Si is the ith superpixel, n is the number of superpixels. Each superpixel is either visible or hidden. The word used for hidden is masked, or you can say off. For this visible, it is on with no masking. This is an image segmented into 50 superpixels. Head region comprises of superpixels numbered S1 through S8, whereas the body S9 through S20. Tail has S21 to S28. Though here tail is not visible, but it is like a sample of how LIME divides the image into superpixels. Finally, we have a background with S29 through S50 superpixels. The procedure is here. Step number 1, it segment images into superpixels here and then generate many new images by turning superpixels on off. This process, as you know, is called as perturbing. So it perturbs several images having these superpixels on off. and we pass all of these to the complicated black box model, which is CNN in this case, because CNN is a model useful for working with images. Here we are working with images, and we obtain the accuracies, let us say 96%, 90, 72, 12 for various images. If suppose it perturb 100 images, it generates 100 accuracies. Finally, as you know, it builds a simpler model. It trains a simple weighted linear model for local explanation. And when we obtain the here uh, coefficients, this beta values we obtain, no? So those beta values represent the importance. If this head superpixels region, this one, if the beta value is 0.92, that is nothing but the weight. If the weight is 0.92, it means it is the most important region in the image for prediction as a class, as a cat. And body region coefficient value is 0.61, where we can classify it to be important. Tail is somewhat important, but background is almost not important. With these coefficient values, we can conclude that this head region is the most important. And here an example walkthrough here. This is an image, original image, all the superpixels are visible. Head, body, tail, background. You can say all are checked. All these 50 superpixels are on. In image 1, superpixel that represent the region tail is off, is masked, and the prediction is 96%. Going forward, we can see that the superpixels corresponding to head and background are masked, and the CNN gives us 72% accuracy, and this goes on for a few hundreds or thousands samples. And here you can represent this in this form as well. If all are on, if all the superpixels for all these regions are on, the prediction is 98%, let us say. Similarly, here you see wherever there are green tick marks, it is 1. Wherever there are red cross marks, it is 0. Means those superpixels were not considered in that image. The advantage is Lime works with any CNN, as Lime is model agnostic. It can work with any type of a CNN model. It is easy to visualize. It provides local explanations. Limitation is it has different runs, may generate slightly different explanations. When you make multiple runs of CNN with various these masked superpixels, sometimes results might be little different. It is not mandatory that always CNN will give us 98% accuracy only for all these, for this one 96 only. And also it depends on the image segmentation quality. Um, it requires image segmentation to be very strong, because we are segmenting the regions in the form of superpixels. The key takeaway for Lime is that it explains a single prediction by approximating the complex CNN locally with a simple interpretable model using perturbed versions of the image. This is Lime for images. We have another a basic method which is called as vanilla gradients. Students, please recall the gradients. In gradient descent, we have a one weight updating formula that says that new weights is equals to old weights plus a learning rate multiplied by the partial derivatives of the output with respect to the weights, and we follow a chain process. Okay, and we continue with w1 upon w2, w2 by w3. In this manner we continue our back propagation from the last output layer back to the first layer where we have weights. So please remember this concept. Gradients generation is very important. Vanilla gradients compute the gradients of the output score with respect to every input pixel. Just now what I said, I described a back propagation in which it generates the gradients with respect to uh, the weights. Here in vanilla gradients, we don't use weights, rather we generate the gradients with respect to um, input pixels. In this image, we have input pixel. So what we do is we generate the gradient. We have the output score. So let us say partial output by that partial pixel value, input pixel value. That is the formula. Here it is there. No, mathematical formula is here. So partial yc is what our score of the class by partial x, where x is the input image, means it performs for all the pixels. This is our s. S is the saliency map. Um, this is vanilla gradients. As we progress, we will understand, we will improve this process, and this will evolve, okay, until we reach the deep lift. Please again S is equals to, S is the saliency map, which is the output of the vanilla gradients method for explanation. This is equal to this partial yc by partial x, which means that here we are generating the gradients. How much the class score changes when each pixel changes slightly. So if you change the pixel here, what is the change in the output score? This yc is the output score. When you change x, you observe what is the change. S is the saliency map, yc is the score of the output class, x is the input image pixels, and this d is the partial derivative. The interpretation is, if changing one pixel changes the prediction significantly, its gradients becomes large. Large gradients means important pixel. A small gradient means unimportant pixel. This is the overall idea of vanilla gradients. Let us look at how it works. First step is in the forward process. When you talk about neural networks, it has two passes. In the first pass, which is called as a forward pass, we move from the input to the output, and that is from left to right. And in the backward pass, we move from right to left. Here in the first step, when you are giving a input image to the CNN, you take the forward pass in order to make the prediction. Once prediction are made, from second step onwards, we try to explain the predictions. So this is forward pass. And after forward pass, consider our input image is this cat image. When we do the forward pass, CNN predicts cat 98% accuracy. Let's choose output node for C. What is the output node for C? Let us say, if it depends on how many classes this CNN can predict. Let us say if you have cat, dog, rabbit, means three classes. If you have cat, dog, rabbit, tiger, lion, deer, and rat, let us say some other various animals. So this can be a binary classification problem, multi-class classification problem. So how many nodes you will have in the output layer depends on the how many classes you are going to predict. Let us say if you have here in this example 3, whatever is the score, whatever you get the score for the cat class, that score is yc. And then in step number 3 we back propagate gradients. We compute the gradients of yc with respect to every pixel. Every pixel value means this image pixel values. In step number 4 we compute this uh, derivatives, means this gradients for every pixel, and we obtain this kind of a gradient value map which is called as our saliency map. Take absolute value and normalize. When we take the absolute values of all these gradients and normalize, we obtain the saliency map. And if you color code the gradient magnitude, we get in color form. You look at in step number 4, we can see it is a black and white. But in step number 6, we have color. If you color code the gradient magnitudes, we get the color. And if in this coloring mechanism, red color means a high, very important. It is the highest importance value is given to the red color. Next, yellow color, and you uh, go down to various other colors where blue colors are not so important. Here you can see you have red color and yellow color, and you have blue color, which means that the model has focused this region to predict the input image which I am pointing is a cat image. Here gradient magnitudes are given, very high red, a little bit orangish high, yellow medium, this blue color, green color low, and blue color very low. When we get these gradient values, let us say I gradient is 0.015, nose gradient is 0.014, whiskers gradient is 0.013. This indicate how important these regions are. Why some regions are said to be important? Because changing these pixels drop the prediction a lot, which means it results in large gradients. And changing the background pixels hardly affects our prediction. Therefore, our gradient value, the gradient value which are numbers which we obtain are small. And here this is with one pixel change example. Let us say pixel value is 120. If you increase the pixel to 121, the prediction of class score from 0.98 has turned out to be 0.995, which means this region, this pixel is of very high importance, and its gradient also changes and increases its value. Pixel in grass, if we pixel value is 150, if we increase to 151, there is no such big impact in this. So change is very negligible, very small, 0.001. I pixel, when we put 0.995 minus 0.980 divide by 121 minus 120, when you do this, when you take the derivative, you obtain this 0.015. Here it is 0.001. Okay, here this. Okay, the advantage is it is very fast, it is simple to implement. The limitations of this, it is noisy, it is sensitive to small change, and it is difficult to interpret. High values can be scattered. Vanilla gradients show where the model looks, but not whether the highlighted evidence is positive or negative for the prediction. So it is sensitive because directly it is working with the input pixels, and it is somewhat difficult to interpret. This is the limitation of vanilla gradient. Because of this limitation, what we are doing, we are trying to get a new method where it combines the gradient with the input. In this, input by gradient improves vanilla gradient by multiplying the input pixel value with its gradient. It considers both pixel intensity, what is there, and sensitivity, how much it matters. Both must be high for the final attribution to be high. If you look at here we are in our last method. The formula was just limited to this dyc by dx, where here there is addition of x multiplied with this element wise multiplication with this gradient values, that gives us input by gradient. If a pixel has high intensity and high gradient, only then it is very important for prediction. The steps is, first step, input image, again forward pass, it predicts, and we compute the gradients and we multiply the gradients with the input pixel values. First we obtain the gradients, input by not input, output by input pixels, and again we multiply with the input pixel. So input pixel value is used twice here. Here you have x input pixel values, and you obtain the gradient value from here, multiply with x. So after obtaining, you multiply here. When you multiply, when we get a large product, it means the pixel is very important, and we can conclude that that is the pixel used for making predictions. Okay, here also we have a simple numerical example. Suppose I pixel is 220 and gradient we obtain is because our we obtain the output cat. Let us say cat score is, let us 0.98, let us say. So 0.98 divide by, not divide, yeah, by actually d 0.98 by d, the pixel value is 220. When you perform this operation, you obtain the gradient, let us say, which is 0.020, and you multiply again with the input intensity, pixel intensity, so you get 4.40, which means that it is of more importance. So eyes, very important, nose, also important, whiskers, little less, ears, more less, body, grass, and sky, very less. Okay, input, this is input by gradients. You have next guided back propagation. Again, this improves. It modifies the back propagation through ReLU layers by allowing only positive gradients to flow backwards. Negative gradients are discarded. Please recall a ReLU activation function. The formula is input max of input comma 0. So whichever is maximum, it chooses that, which means it will discard the negative values. If the x value, max of x comma 0, if x is negative, so it chooses 0. If x is positive and greater than 0, it chooses x value, that is ReLU. Here it is given, a ReLU of z is equals to max 0 comma z. So ReLU's main functionality is to discard the negatives and pass only the positives forward. Guided back propagation modifies the back propagation. We know back propagation algorithm. In that we are adding one more step. That step is nothing but the ReLU. So in that ReLU, in the forward pass also we use ReLU. In the backward pass also we use ReLU. So how we use, we forward only the positive values and we just discard the negatives. Here there is a mathematical formula. Here we use if x is greater than 0 and x of L plus 1 means next layer, R super L. R super L means gradient at layer L, which is the current layer. R L plus 1 means gradient from the next layer, which is L plus 1. X super L means activation at layer L, which this we obtain from forward pass. And this is a function, indicator function. Greater than 0 means it allows only positive values. In both the ways, it is allowing only positives. Let us look at an example. Here input is 5, ReLU output is 5. Is it active? Yes, because it is positive. Here input is 2, output is 2. This is also active. Where when we get input -1, ReLU gives us from this max 0, z, it gives 0. So ReLU output is 0. Is our active? It is not active. This is also not. This input is not active. These two inputs are not active because they are negatives. A guided back propagation rule is gradient passes only if activation is greater than 0 and also gradient should also be greater than 0. Activation is what we get from the forward pass. Here we are also considering the gradients. Gradients must also be greater than 0. Only then we pass. This is forward pass. This is cases at the ReLU neuron. This is activation and this is incoming gradient. And here because it is this activation is 5, input gradient is also plus 0.8. Both are greater than 0, therefore both are active and both will be passed. Whereas in the second case, activation is negative and incoming gradient is positive, it will not pass. Here activation is positive and incoming gradient is negative, this will also not pass. Finally both are negatives, both will not pass. So let us say I pixel value of I, and after pixel and gradient and doing all that step, we obtain this positive 0.8. This is positive and this here activation is 6. Both are positives. So this passes. This passes means what? This is important. This pixel or the region is important. Ears also important. It is passing. Whiskers also important. Grass, sky not important because in one of the values we are finding negative. Because it is negative, we don't allow it to pass forward and therefore we don't use it. For explanation, why we should use this guided back propagation in vanilla gradients, we use only this dyc by dx, which it allows both positive and negative gradients to flow. So because of which it can produce noisy visualizations. Negatives means which are not important. Whereas this guided back propagation, it is using two filters. Activation as well as gradient. Both must be positive. Only then it passes. Therefore, here we can conclude that it keeps only positive evidence and it produces sharp and clean visualizations. Only when both the activation is positive and the gradient is positive, the gradient is allowed to flow backward. So in back propagation, gradients will be flown backward to the next layer Next layer means in towards the left, only if it is positive. The advantage is it produces sharp visualization. The limitation is it is not class discriminative. We are not considering any class, this is not class discriminative. Here the step-by-step algorithm for guided backpropagation: input image, CNN, forward pass, compute activations, backpropagate gradients, check whether both are positive, only then they are passed, and this you repeat until the input layer. That will generate a high resolution explanation which is called as guided backpropagation map. This I explained to you last class. Now I am directly jumping on to GradCam. GradCam highlights the image regions that contribute most to a specific class prediction by combining gradients with the feature maps of the last convolutional layer. Suppose this is an input image and this is our convolutional neural network. Let us quickly revisit. This is our convolutional neural network which contains convolutional layers followed by ReLU activation function and max pooling, and these three are repeated. Which three? Three here means convolutional layer, a ReLU layer and pooling layer. These three occurs n number of times depending on the architecture of the CNN. In this example, they are occurring 3 times. So after this, the last convolutional layer, we obtain feature maps. Feature maps we obtain after every convolutional layer. However, to understand GradCam, we are concerned only with the feature maps that we receive after the third convolutional layer in this example. In general, I can say that the last convolutional layer. Let us consider here whatever are shown are the feature maps from the last convolutional layer. After that, we get either global average pooling or we get flatten, and then we get a fully connected network. This one, fully connected. From there, we obtain the score. Based on the score, we predict whether it is a cat or a dog, whichever neuron here, the output neuron is giving us the highest weight or the score. We predict the output to be belonging to that particular class. Okay, please understand here, this is a image, this is our convolutional layers, layer 1, layer 2, and we reach the last convolutional layer. We are now concerned only with the feature maps which are denoted here by A, K. Okay, and because we will have after each convolution layer, we will have K number of feature maps. It depends on how many kernels we are using. Here let us say if we use K kernels, we get K number of feature maps, A1, A2 up to AK. Once we obtain the class score, we backpropagate the class score which is YC, and we obtain the gradients with respect to the feature maps of the last convolutional layer. You see how we are evolving. In the first method, we saw the output with the gradients with respect to the input pixels. Then we saw output with respect to input element wise multiplication with input pixels. And then we saw how backpropagation can be modified to allow only positive gradients to flow. And here now we have come to this method, which is gradcam, where we are taking the gradients of this our output class with respect to 1 minute, students. Hello? 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 वालेकुम सलाम आयशा। आयशा, मैं क्लास ले रही हूँ, मैं क्लास लेने के बाद कॉल करती हूँ। ओके डियर, at 5 o'clock I will call you. Okay? So we are here. So we are taking here obtaining the gradients. Let us look at the process, and then we will look at numerically as well. In the first step, we find the class score through forward pass. In the second step, we compute the gradients, this formula. Alpha C super K, this is importance weight of feature map K for class C. Whatever is the predicted class C, that Z means Z is nothing but height into width. Okay, height into width. AK is kth feature map from last convolutional layer. A K and sub ij means pixel at position ij in feature map K. Yc is the score of the output class, and here whatever we obtain are this one is the partial derivatives which gives us the gradients. This is the second step. In the third step, we compute the heat map. Please understand the formula of the heat map. We use ReLU, and we take this AK is the kth feature map. This alpha CK is the importance weight of feature map. ReLU, it keeps only positive importance, negative value set to 0. And you take the summation for every feature map. Okay, K means K number of feature maps. If you have 10 feature maps, you perform this operation 10 times. If you have 5, you perform for 5. And ReLU means, it passes only the positive values. And then here we get the heat map. Feature maps that are more important for class C will contribute more to the heat map. This is the intuition. Let us look at it numerically. In the first step, we have to make a forward pass. Input image is passes through various convolutional layers and reaches the last convolutional layer. Though every convolutional layer generates kernels and feature maps, here we are concerned only with the last layer. So here last layer is shown in dark color. We have these kernels, and these are the feature maps that are generated. They are numbered like A1 through AK. And GradCam uses the feature map from the last convolutional layer because it typically has the most high level semantically rich features. Why only we are using last convolutional layers? Because it has semantically high features. And from here onwards, next 4-5 slides I have taken from Neptel. Here these are very good number of features. Semantically rich features you can find here. Where earlier layers capture only the edges and textures, um, low level features like lines and contours and you know edges. GradCam needs high level semantic features, hence it uses the last convolutional layer. Now we pass the input image through the CNN to get the feature maps from the last convolutional layer, and the raw output scores YC, which are called as logits. Okay, logit is called as the score, the class score before the softmax. Here you can see we obtain these feature maps, and then we have a flattened layer. We have a dense layer, which is nothing but a fully connected network useful for performing classification. And here last layer is our softmax layer. Before softmax we have this YC, which is the logit or the output score. This is first step. In the second step, we compute the gradients with respect to the last layers feature maps because they capture semantically rich features, and we have gone through this formula. Let us look at this. Let us say there are 3 feature maps, A1, A2, A3. For these 3 feature maps, we have to compute the gradients. Here, let us take A1. A1, its dimension is 5 by 5, height 5, width 5, 5 by 5. And we are trying to get YC. We have a YC, no, which is our logit, the score. This D YC by D A1 I comma J. So we will take YC by 2. We will obtain, let us say, 0.2. YC by 1. We will, let us say, obtain 0.1. So these are in green color box are the gradients which we have obtained on the logit with respect to the feature map values. Once you obtain these gradients, next step, see, this part is completed. So what is second part? Second part is summation. So we add all these row values, 0.2 plus 0.1 plus 0.0 plus 0.2 plus 0.3. We get 0.8. Okay. Similarly, we add along all the horizontal axis and the vertical axis. Okay, means row wise, column wise. I and J we have to do for both row wise and column wise. Once we get all these, we have to take the total gradient sum, which is this 3.3. Okay, and Z value is 25. So here Z value is 25, and this entire equation is giving us 3.3. So we have to put here, take 3.3 divided by 25, we obtain 0.132. So this A1 or alpha 1 score is 0.132. Similarly, we have to do for A2 and A3. Let us say A1 is 0.132, A2 is 0.052, and A3 is 0.3. And if the gradient is large and positive across many locations in AK, what does it mean? This feature is very important for class C and thus gets larger weight. Here, out of these 3, which is having the larger weight? You see here A3 is having the larger weight because it is 0.3. If gradients are small or negative, that feature doesn't help. for class C and gets smaller weight. Let us say, look at here, this is a smaller weight. Okay, second step is completed. We have obtained all the gradients. In the third step, we have to create a heat map. Heat map means we highlight those pixels that are contributing more in the prediction. The formula is here as we saw earlier. Small ak multiplied by capital AK. Capital AK denotes feature maps, small ak denotes the gradients. You multiply for all the feature maps. Then you get this um, localization map or a weighted sum, which is called as a heat map. Let us look at numerically. We know A1, what is the value of A1 and A2, A3. And small a1, which is nothing but the gradients, also we know 0.1, here it is 0.05, here it is 0.3. Now we have to, what we have to do, we have to perform multiplication. This 2 into this 1, 3, 2, and then what we have to do is we obtain this here, this multiplication for one feature map, and then we have to do this for all the feature maps. When you perform this for all the feature maps, you obtain one visualization map, GradCam before ReLU. Okay, after once you do this, you even have to pass it through ReLU. So this is the feature map which we obtained by multiplication and then addition of all. So the 0.2 plus 0.05 plus this 6. Okay. So you have, when you add all the element wise addition, when you do, you get these values. Okay. So now this you pass through ReLU, and what ReLU does is ReLU will choose only the positive value. In this example, we don't have any negatives. But suppose if you have also, it will not choose. After choosing, it creates this map. This is called as a heat map, where we get this can also be called as a heat map, where the highest values, the larger values, are considered to be most important, and we consider them to be the influencers for predictions. Here you can see this value is 0.9, 0.97, 0.89, 0.8. So these are like influencing more. These are pixels. Here also we have pixels with less influence, here zero influence. Let us say this is our original image and this is our grad cam that we obtained by that process. We are applying the color coding based on, we know no, a red color means which is having a higher value, and so on. After color coded all these values here, let us say we obtain this. When we obtain the GradCam heat map, it is smaller in dimension compared to the original image, because no, in CNN we perform max pooling and we reduce the size of the original image. Because of that, our last layer feature maps size is less compared to the original. We have to perform another operation which is called as upscaling. In upscaling, we increase the size of our heat map to be same as our image size. And the last step is overlay. Overlay means you just put this heat map upon the original image. When you perform this overlay operation, you can find which are the regions that are most important in the identification of the class cat for this image. The GradCam heat map is much smaller than the input image because the final convolutional layer input map is much smaller than the input image. We have to resize, which is called as upscale, the heat map to the same size as the input so that it can be overlaid on the original image. After resizing, overlay the heat map on the original image. The resulting visualization highlights which regions of the image were most important for the model's prediction of class C. This shows where the network looked when making its decision. So our CNN network has looked at this region to predict that it is a class, cat class. Okay, so this is also the same. We have to up sample and overlay. CNN ends with convolution layer, then flatten, then dense layer, then softmax. After flattening, spatial structure is okay. Here one more important point to be considered: why we are choosing only last convolutional layer, why not flatten layer? Because until the last convolutional layer, our image is in 2D space, whereas flattening means it converts that 2D space into 1D vector, and 1D will lose the spatial information. That's why we have to choose the last convolutional layer. Okay, I hope it is clear. Next method is guided GradCam. It combines GradCam with guided backpropagation. This is the formula. We obtain the gradients and we obtain the heat map, and here our idea is that we should pass only the positive gradients. GradCam provides a class specific location mask where we know where to look to get to the class prediction. Guided backprop provides high resolution gradients. Okay, guided backpropagation provides gradients, and when you combine both, we will get a very crisp and sharp output, and that's why we are using this guided GradCam. Now, why we should use a guided GradCam? Because GradCam tells us where, means where our model has looked at to perform prediction. Guided backprop tells what details. These are very sharp edges, and when you combine both, it looks better. That's why we are combining in a method called as guided GradCam. Then we have another method which is called as smooth grad. It reduces noisy saliency map by averaging gradients computed from multiple noisy versions of the same image. It keeps important signals and remove noise. Sometimes while doing this process, you obtain the noise. When you obtain the noise, we have to reduce it by following this formula in smooth grad, which is this here. In earlier formulas, we had dyc. Here we have dfx plus ni, where we have this random Gaussian noise. We are adding the random Gaussian noise to the image, and n is the total number of noisy samples. X is the original image. CNN prediction is f is the CNN prediction, and we obtain the gradients of the output with respect to the input by adding some noise. When you add a noise and then you obtain the gradients, and then we try to make the model learn such that it can make a smooth edges, smooth image. We start with the original image, add some random noise to create many noisy copies, Compute the gradient for each noisy image, average all gradient maps pixel wise. The resulting map is a smooth grade saliency map. Here example, what is the difference between vanilla gradient and smooth grad? Vanilla gradient, we have only one gradient, whereas in smooth grad, like how lime is perturbing images and finding the prediction. Similarly, smooth grad is adding a little noise and then obtaining the predictions. So a smooth grad average of 100 gradients. When you have so many gradients and you average out the gradient values, you obtain a better quality image. So here this is our original image. Noisy samples, slight noisy means very slight changes. You make slight changes and you compute the gradients for each noisy image, and then you average the gradients pixel wise. And why noise disappears consistently high across images, whatever regions are consistently high across all the images, they will have a higher value. When you have a higher value, it means that they are the indicators of the predictions. Means our explanation prediction is also better. The quality of the explanation image is better. So this is the complete smooth grad algorithm. In the first step, we have original image. Second step, we create by adding Gaussian noise, we create several samples. We perform forward pass, and then we compute the gradients, and then we average all the gradients, and whichever region is giving a high gradient value. Look at here, this is so sharp. This is better than before, and this saliency map is better than before. So here vanilla gradient is one shot measurement, it is sensitive to noise. Smooth gradient, many measurements, average is stable, signal stays high, and random noise cancels out. True important regions keep giving high gradients in almost every noisy image. Noisy regions change randomly from image to image. Averaging keeps stable. Means the values are stable and reduces the fluctuations, which are noise. The advantage is it is cleaner saliency maps. It reduces noise effectively. It is easy to implement. It is simple averaging, and limitations is it requires multiple forward and backward passes. Obviously, when you are doing for various images, you have to do many forward and backward passes. Therefore, computational cost increases. The key takeaway is smooth grad computes many gradients from slightly noisy versions of the same image and averages them. Therefore, we obtain a smooth image. This is the last method, which is deep learning important features. It explains a prediction by comparing each neuron's activation with its activation for a reference. Means there will be a reference baseline model means using which we can compare others. So it explains prediction by comparing each neuron's activation with its baseline activation, and propagates these contributions differences backward through the network. The key idea is instead of asking how sensitive is the output to a tiny change, means gradient is the change. No, gradient is nothing but the change. How much change? Okay, it gives when you make a change to something else. Deep lift asks how much did this input feature change the prediction compared with a reference image. Okay, there is a reference image. Here this is our baseline image. This is a blank black image. And CNN has made a prediction that it is a cat of 5%. Okay. It may be less than that. It is just like one small value. And our actual image is this. cat image, and here CNN is predicting 98%. So how much is the change? The change is 93%. 93, because here you see, uh, even here you compute y with respect to this y and this y, means yo is this baseline and this prediction of the original image. The image increases the cat score by 0.93. Deep lift attributes this increase to image regions, which are pixels, features. This is here there are no pixels, nothing is there. There is another type of method, you know. So we measure the contribution of input feature I to the change in output. Here contribution of input feature, actual input value pixel, xi is the actual input. This baseline reference input, here this is the change, that is the change in input relative to the baseline. Y is the model output, and model output for baseline, change in the output. And these are pixel examples. Complete deep lift workflow. Here choose baseline image, input actual image, compute change in the image. Here also we are computing the like sort of um, first we are doing this subtraction, and then we back propagate activations. So we compute activations, back propagate through the network using deep lift rules, assign contribution or to each input pixel, and create contribution map. Here divide the image into regions. Deep lift contributions we can find by using various regions. This is vanilla gradient, this is deep lift. It highlights only important regions. Background receives a small contribution. Deep lift explains how much each input feature increased or decreased the prediction. You add something and check how much it is increasing, and then you remove some that particular thing and you see how much it is decreasing. Okay. Why deep lift is useful? It handles zero gradient problem better. Even if gradients are zero, deep lift can still give meaningful contributions. Meaningful feature contributions, class specific explanations. The advantage is it handles zero gradient problems better than standard gradients. It provides meaningful feature contributions. Limitations, it results depend on the choice of the baseline image. Requires specialized back propagation rules. These rules must be very complex. This is a summary of all the explainable methods for images. ROI is not exactly the method, rather it is the identification of the important regions that will contribute to the predictions. Here lime, it perturbs image pixels and create a simple model. This vanilla gradients, it compute gradients of the class score with respect to input pixels. This is same, it computes gradients with input pixels and it multiply by input. This allow only positive gradients to flow through the network using a ReLU. This one GradCam, it generates class specific heat maps. This guided GradCam, it combines GradCam with guided backpropagation. Smooth Grad, it averages gradients from many images. It creates multiple images, variations of images by adding little noise. And finally Deep Lift, it compares activations with the baseline input. Base A1 image you give, and then you check how much it is this feature is contributing how much, and it propagates the contribution difference through the network. These are the formulas. Please remember the formulas. That's it.